It says compute each sum below. Give exact values. And we know that they are actually infinite geometric series. And we're going to be able to identify those. We're going to be able to identify these are infinite geometric series. I'm actually going to give a formula that I like to use for an infinite geometric series. And that is the summation of r to the k with the index starting at k equals 0 to infinity is simply 1 over 1 minus r. As long as what? As long as the absolute value of r is less than 1 and greater than 0. So I'm going to try to get this first geometric series into this form. How do we do that? Before I get started, I might as well tell you what this geometric series looks like. This looks like 1 plus r squared plus r to the third. Whereas 1 is really what? 1 right here is r to the 0 power. So this is r to the 0, r to the first, r to the second, r to the third. Remember, 1 is r to the 0 power. It'd be nice to get this 1 to show up in here. There's actually a greatest common factor here. So instinctively, your algebra skill says factor out a 2 times negative 3/4. And then what is left? I'm actually going to draw it in a bracket. We have a 1 plus negative 3/4 to the first power plus, now we're at the third term, we have negative 3/4 to the second power. And this doesn't stop. Notice this pattern here is this pattern right here. So now you can see the common ratio. It's actually negative 3/4. Let's write this into summation notation. Here's where everything gets really, really cool. So this is the summation of k equals 0 with a common ratio of what? Negative 3/4 raised to the k power, and then we run that to the concept of infinity. We are now ready to substitute. This is equal to negative 3/2 multiplied by 1 over 1 minus r, but r is negative 3/4. I really want to take care of these fractions in the complex fraction. So if I multiply by 2 over 2, we get something really, really nice. We get a negative 6 in the numerator, and then we get 4 plus 3. Yep, we get a 4 plus 3. So our final answer is negative 6/7. That's the answer to part A. Make sure you show all your work. Part B. Let me divide the page here. Part B. Well, once again, in part B, there's a greatest common factor. Why don't we factor that out? It's a 3. And now we have a summation of j equals 1 to infinity of 3 raised to the j power. So our index is j equals 1. I should say our starting index is j equals 1. It'll be nice to start that at 0. So why don't we do a shift. Why don't we do something like this? We are going to replace j equals 1 with a j plus 1 here. So imagine if you replace j with j plus 1. Replace j with j plus 1, what would happen? Let me do this in slow motion. So here's your j. Off to the side here, we're going to replace j with j plus 1. So if you do that, the j plus 1 equals 1. Now you get an index of j, starting index of j equals 0. So that's great. Let's see what that looks like. Summation. Now we get j equals 0. 3, and replace j with j plus 1. So this is j plus 1. Those are equivalent summations. We once again have a common factor. The common factor is another 3. 3 to the first power times 3 will get you 9. And now we're ready to substitute. 9 times what? 1 over 1 minus 3. Ooh, I'm working way too hard. When I got to here, I need to stop. How come? How come when I got to here, I need to stop? What is the absolute value of our common ratio? Absolute value of r is equal to the absolute value of 3, which is greater than 1. That is not good. Why is it not good? Because it doesn't converge. It does not satisfy this formula. What's our conclusion? Therefore, this series has no sum. The technical term for this is the series does not converge. It does not converge to a finite number.